All right, what are we up to today? So previously, this week so far, we have been talking about elementary number theory. And today, we will be talking about a very nice application of elementary number theory, namely cryptography. So a couple of quick introductory remarks that I will not write down. This is a really interesting subject because using number theory for cryptography is one of the best examples of pure math being developed totally independent of applications and then turning out later to have very surprising and very important applications. So the kind of number theory that we've been talking about, no one had this in mind, what we're about to talk about, when they were developing these theories. But people later discovered that all this work that had been done turns out to be extremely useful. So it's a very cool example of this philosophy that having a vibrant mathematical culture is useful in ways that are hard to predict for science and for technology and all kinds of things. But let me temper this a little bit by saying that it leaves something to be desired, that cryptography is kind of the only example, at least for number theory. Number theory, it is pretty much the only application. And so if you spend much time doing number theory, you will hear people talk about it again and again, but you will not hear them mention any other applications because there do not appear to be any. So, there's you can think about it both ways. But I will say that, so cryptography is very important if you're into computer science or applied math. It's really essential for, everything that computers do. But it's also important if you're interested in number theory from a pure perspective. So I do research in pure math in number theory. So my research is completely unrelated to applications to cryptography and things like this. But I am still interested in this stuff because it is how you convince the government to give you money. And that's very important for pure math as well. So let's start then. So we're going to talk about a basic example just to fix some ideas, which is shift ciphers. So this is just to get on the same page with what we're talking about with cryptography in general. So the idea of cryptography is we want to transmit a message without worrying about people eavesdropping. So the idea is that we're sending this message and we think it might be intercepted by someone, and we want to make sure that they can't read it, even if they find the message. So we're going to make it secret somehow. And the basic idea is that we send it in code. So we send an encrypted message which the recipient will decrypt. So this will all become more clear when we do an example. So a shift cipher works like this. One of the more basic ways that you can encrypt something. So pick a number. Say 3. We'll work with 3. And replace each letter in your message with the third letter in the alphabet after it. So let's say we want to send the message help using a shift by 3 cipher. So for each letter, we're going to turn it into a different letter by looking at what's the third next letter in the alphabet. So H, I, J, K is how the alphabet goes right there. So H becomes a K, like that. And similarly, E, what is the third letter after E? E, F, G, H becomes an H. And then L and P, we use the same idea. L, M, N, O. P, P, Q, R, S, S. So the encrypted message reads KHOS. And as you can see, if someone finds this message, they will not know what it means unless they can, unless they know how we have encrypted it. So this is the message that we send to the recipient. And then on their end, they decrypt it and they can read it. So this send to recipient. And let's say we receive a message back. And let's say that message reads RPZ. So this message is encrypted using the same code. Let's decode it. So to decode, to decrypt, shift by -3, which just means take the third letter preceding it in the alphabet. So R, let me draw it this way so that it's facing sort of the same direction. R is going to turn into, I have a much harder time going backwards in the alphabet, which I think is understandable. But I have it written down, O, P, Q, R. So it goes to O. And then P, what is the alphabet in this piece? It is M, N, O, P. So this goes to M. And then Z is W, X, Y, Z. So this goes to W. So the decrypted response is OMW, which tells us that help is on the way. Excellent. So this is essentially how a shift cipher works. Let's clean it up and reformulate it in terms of numbers. So it's clean and maybe allows us to do these computations faster. For example, if we're working with a computer, we can work with it more easily if we translate it into numbers. So we're going to say A is 0, 0, B is 0, 1, C is 0, 2, etc. Down to Y is 24, and Z is 25. So there's 26 letters in the English alphabet, which if we start from 0, gets us up to 25. And quick note, why do we use leading zeros when we only have one digit? And that's just to help us identify what are each letter. So in this way, we have each block of 2 characters represents 1 letter, instead of letters being possibly 1 or 2 digits. Always 2 digits. So our message, H-E-L-P, if we do this translation, turns into 07, 04, 11, 15. So we can think of it as being a number rather than a string of letters. And again, we may have a leading 0, but that won't affect any of the computations. We just need to keep that in mind when we're encoding and decoding things. So if we get some message back and decode it and find that it's the wrong number of characters, that's just because we're missing a 0 at the front. Things like this can happen. Which, you know, we don't need to worry about too much, but when you're doing actual examples, is good to keep in mind. So now that we have our message as a number, we can talk about what it means to encrypt and decrypt things in this setting. So to encrypt this message, we split it into blocks of 2 digits, because each one of those represents a single letter. And to each block of 2 digits, we apply the function, which I'm going to call E for encrypt. E of M is M plus 3 mod 26. So the mod 26 is saying that our shift cipher wraps around. If we want to encode something like Y, this would become Y, Z, and then you start back around from the beginning, A, B. So Y would become B. And this corresponds in our mod 26 to 24 plus 3 is congruent to 1 mod 26. All right, and 1 is a B. So this is just, you know, simply a translation of this letter shift into numbers. So this is our encryption function. Split it up into blocks of 2 digits and apply this function. And to decrypt, to each block of 2 digits, apply the decryption function, which is just M minus 3 mod 26. So this is how we can formalize it mathematically. And this may or may not make it easier to work with in this context, but in the more complicated context that we're about to talk about in a second, it will be, you know, totally essential to treat them as numbers because we're going to be doing arithmetic with them. So a couple more pieces of terminology. The key is the secret information that you need to encrypt or decrypt a message. In this case, it's the number 3. Because that's the thing that's determining the shift. If you know that it's a shift by 3, then you can encode and decode things. And just a couple more words. You may hear the unencrypted message called plain text, and the encrypted message called ciphertext. So these are the basic ideas of cryptography.